Welcome to our exploration of intelligent agents in artificial intelligence. In this chapter, we'll dive into what makes an agent intelligent, how it interacts with its environment, and why these concepts are foundational in AI. We'll also discuss rationality, autonomy, and the different types of agents you'll encounter, from simple reflex agents to learning agents. By the end, you'll have a clear understanding of how agents perceive, decide, and act to achieve their goal. Let's begin by defining what an agent is and why its environment matters so much in the world of AI. The heart of any artificial intelligence system is the relationship between an agent and its environment. An agent is anything that can perceive its surroundings through sensors and act upon those surroundings using actuators. The environment, on the other hand, is the external context in which the agent operates. This dynamic interaction is what allows intelligent systems to function and adapt. Whether it's a robot navigating a room or a software program managing emails, understanding this interplay is crucial for designing effective AI solutions. Let's break down the main components that make up an intelligent agent. First, there are sensors. These devices detect changes in the environment and relay information to the agent. Next, actuators are responsible for converting energy into motion, enabling the agent to interact with its surroundings. Effectors are the actual devices that carry out actions such as motors or gears. For an AI agent to function effectively, it must follow four key rules: perceive its environment, use observations to make decisions, ensure each decision leads to an action, and always act rationally to achieve the best outcome. To ensure intelligent behavior, AI agents must adhere to four essential rules. First, they need the ability to perceive their environment accurately. Second, these observations must inform their decision-making process. Third, every decision should result in a concrete action. Finally, the action taken must be rational, always aiming for the best possible outcome. These rules form the backbone of how agents operate, ensuring that their actions are purposeful and aligned with their objective. By following these principles, agents can adapt and respond effectively to changing environments. Agents come in many forms, each with unique sensors and effectors. Take a human agent. Our eyes, ears, and skin serve as sensors, while our hands, legs, and mouth act as effectors, enabling us to speak, walk, or write. Robotic agents use cameras and infrared sensors to perceive and motors and gears to move or grasp objects. Software agents, meanwhile, rely on keystrokes, file contents, and network data as input, and can output through displays or send packets, managing emails or monitoring systems. These examples highlight the diversity and adaptability of agents in different environments. Let's look at how different agent types function in real-world scenarios. Human agents use their senses to interact with the world, performing tasks like speaking or writing. Robotic agents equipped with cameras and sensors can move and manipulate objects. Software agents operate in digital environments, processing data and automating tasks. Each type of agent is designed to perceive, decide, and act within its specific environment, demonstrating the flexibility and power of intelligent systems across various domains. Key distinction in AI is between the agent function and the agent program. The agent function is an abstract description of how an agent should behave, mapping any sequence of perceptions to an action. The agent program, on the other hand, is the concrete implementation of this function, a real algorithm running on hardware. For example, in the vacuum cleaner world, the agent function might dictate that if the current square is dirty, the agent should clean it, otherwise it moves to another square. The agent program turns this logic into actionable code. Consider the classic vacuum cleaner world, which consists of just two locations. Squares A and B, the vacuum agent perceives its current location and whether there is dirt present. Based on this information, it can choose to move left, move right, clean the dirt, or do nothing. This simple scenario illustrates how agent functions and programs work together, mapping perception to actions in a structured way. It's a foundational example for understanding more complex agent behaviors in AI. Agent function is a mathematical description that defines how an agent should act based on what it perceives. It maps every possible sequence of perceptions to a corresponding action. In theory, this could be represented as a massive table, listing all possible inputs and the actions the agent should take. However, in practice, this table could be extremely large or even infinite. The agent function provides an external view of the agent's behavior, focusing on what the agent should do in any given situation. While the agent function describes what an agent should do, the agent program is the actual code or algorithm that brings this behavior to life. It runs on a physical machine, processing inputs from sensors and producing actions through effectors. The agent program is the internal implementation of the agent function, translating abstract logic into real-world operations. This distinction is crucial for building intelligent systems that can operate reliably and efficiently in their environments. Rational agent is one that acts to achieve the best possible outcome, or when faced with uncertainty, the best expected outcome. Rationality in AI is not about perfection, but about making the best decisions given the available information. Four key factors influence rationality: the performance measure, the agent's prior knowledge of the environment, the actions it can perform, and its percept sequence to date. By considering these factors, rational agents can adapt and optimize their behavior over time. Rational agent is defined by its ability to select actions that maximize its performance measure, based on the evidence from its percept sequence and any built-in knowledge. For every possible sequence of perceptions, the agent should choose the action that is expected to yield the best result. This approach ensures that the agent's behavior is always aligned with its goals, even in uncertain or changing environments. Rationality is a guiding principle for designing intelligent agents that can succeed in complex tasks. Designing intelligent agents, it's important to focus on performance measures that truly reflect the desired outcomes in the environment. For example, in the vacuum cleaner scenario, the performance measure could be the amount of dirt cleaned in an 8-hour shift. By aligning performance measures with real-world goals, we ensure that agents are evaluated based on meaningful criteria, rather than arbitrary behaviors. This approach leads to more effective and reliable AI system. Omniscience refers to knowing the actual outcome of every action, but in reality this is impossible. Rational agents instead act based on expected success using the information available to them. While an omniscient agent would always make the perfect choice, rational agents strive for the best possible outcome given their knowledge and perceptions. This distinction highlights the practical challenges of building intelligent systems that operate in uncertain environments. It's important to understand that rationality is about maximizing expected performance, not achieving perfection. Rational agents make the best choices they can with the information they have, while perfection would require complete knowledge of all outcomes. Rationality does not require omniscience. Instead, it relies on gathering information and exploring the environment to improve future decisions. This ongoing process is what enables agents to learn and adapt over time. Task environments are the settings in which agents operate and perform their tasks. Each environment presents unique challenges and opportunities, influencing how agents perceive, decide, and act. Understanding the properties of different task environments is essential for designing agents that can succeed in a wide range of scenarios. Whether it's a physical space, a digital system, or a combination of both, the environment shapes the agent's behavior and effectiveness. PEAS framework is a useful tool for analyzing task environments in AI. PEAS stands for Performance Measure, Environment, Actuators, and Sensors. By breaking down a task environment into these components, we can systematically design and evaluate intelligent agents. This structured approach ensures that all relevant factors are considered, leading to more robust and effective AI solutions. First element of the PEAS framework is the performance measure, which defines what success looks like for the agent. This could be anything from the amount of dirt cleaned by a vacuum agent to the number of emails managed by a software agent. By clearly defining the performance measure, we set the standard by which the agent's actions will be evaluated, ensuring that its behavior aligns with our goals. Environment component of PEAS refers to the external context in which the agent operates. This includes all the factors that can influence the agent's perceptions and actions. By understanding the environment, we can design agents that are better equipped to handle the challenges they will face, whether in the physical world, a digital system, or a hybrid setting. Actuators are the components that allow an agent to interact with its environment. In the PEAS framework, actuators are responsible for carrying out the agent's decisions, whether that means moving a robot, displaying information on a screen, or sending data over a network. Choosing the right actuators is critical for ensuring that the agent can effectively achieve its objectives. Sensors are how an agent perceives its environment. In the PEAS framework, sensors gather information that informs the agent's decisions and actions. Whether it's a camera on a robot, a microphone in a smart device, or software monitoring network traffic, sensors are essential for enabling intelligent behavior. The quality and type of sensors directly impact the agent's ability to succeed. Simple reflex agents operate by responding directly to current perceptions without considering the history of previous states. They follow condition-action rules such as if the square is dirty, then clean it. While effective in straightforward environments, these agents struggle with more complex or unpredictable situations. Their simplicity makes them easy to design but limits their adaptability. Model-based reflex agents improve upon simple reflex agents by maintaining an internal model of the environment. This allows them to keep track of aspects that aren't immediately observable, enabling more informed decisions. By considering both current perceptions and stored information, these agents can handle more complex tasks and adapt to changing environments. Goal-based agents take things a step further by using goals to guide their actions. Instead of simply reacting, they evaluate possible actions based on how well they achieve a desired outcome. This approach enables more flexible and purposeful behavior, as the agent can plan and choose actions that move it closer to its goals, even in unfamiliar situations. Utility-based agents evaluate actions based on a utility function, which measures how desirable a particular outcome is. By considering the expected utility of different actions, these agents can make nuanced decisions that balance multiple objectives. This approach allows for more sophisticated behavior, especially in environments where trade-offs are necessary. Learning agents have the ability to improve their performance over time by learning from experience. They can adapt to new situations, refine their strategies, and become more effective as they gather more data. This adaptability is what sets learning agents apart, making them ideal for dynamic and unpredictable environments. Each type of intelligent agent has unique features that make it suitable for different tasks. Simple reflex agents are fast and straightforward, while model-based agents can handle more complexity. Goal-based agents are flexible and purposeful, utility-based agents make nuanced decisions, and learning agents continuously improve. Understanding these features helps in selecting the right agent for a given problem. Autonomy is a key characteristic of intelligent agents. An autonomous agent can operate independently, making decisions and taking actions without constant human guidance. This independence allows agents to function effectively in complex and dynamic environments, adapting to new challenges as they arise. Rationality and autonomy often go hand in hand. An autonomous agent must be able to make rational decisions on its own, using the information it gathers from the environment. This combination is what enables agents to achieve their objectives efficiently, even in the face of uncertainty or incomplete information. For an agent to act rationally, it must gather information and explore its environment. This process allows the agent to update its knowledge, refine its strategies, and make better decisions in the future. Information gathering and exploration are essential for agents that operate in complex or changing environments, enabling continuous improvement. To recap, intelligent agents are defined by their ability to perceive, decide, and act within an environment. Their structure includes sensors, actuators, and effectors, all working together to achieve specific objectives. By following key rules and leveraging different agent types, AI systems can tackle a wide range of tasks from simple to highly complex. The interaction between agents and their environments is dynamic and ongoing. Agents must constantly adapt to changes, updating their perceptions and adjusting their actions accordingly. This continuous feedback loop is what enables intelligent behavior and effective problem-solving in AI systems. Designing intelligent agents comes with its own set of challenges. These include handling incomplete or noisy data, operating in unpredictable environments, and balancing competing objectives. Overcoming these challenges requires careful planning, robust algorithms, and ongoing refinement of agent strategies. Intelligent agents are used in a wide variety of applications, from robotics and automation to software assistants and smart devices. Their ability to perceive, decide, and act makes them invaluable in fields like healthcare, finance, logistics, and beyond. As AI technology advances, the range of applications for intelligent agents continues to grow. The future of intelligent agents lies in greater autonomy, adaptability, and collaboration. Advances in machine learning, natural language processing, and robotics are enabling agents to tackle increasingly complex tasks. As agents become more capable, they will play an even larger role in shaping our digital and physical worlds. As intelligent agents become more integrated into society, ethical considerations become increasingly important. Issues such as privacy, accountability, and fairness must be addressed to ensure that AI systems benefit everyone. Responsible design and deployment of intelligent agents are essential for building trust and ensuring positive outcomes. In many scenarios, multiple agents work together as a team to achieve shared objectives. Collaborative agents must communicate, coordinate, and sometimes negotiate to succeed. This teamwork enables more complex and large-scale problem-solving, opening new possibilities for AI applications. The relationship between humans and intelligent agents is a key area of focus. Effective human-agent interaction requires clear communication, intuitive interfaces, and mutual understanding. As agents become more advanced, designing systems that work seamlessly with people will be critical for maximizing their benefits. Adaptability is a hallmark of intelligent agents. The ability to learn from experience, adjust to new situations, and refine strategies over time is what makes agents truly intelligent. This adaptability ensures that agents remain effective even as their environments change. Despite their capabilities, intelligent agents have limitations. They may struggle with ambiguous or incomplete information, face computational constraints, or encounter environments that are too complex to model accurately. Recognizing these limitations is essential for setting realistic expectations and designing robust systems. Continuous improvement is a core principle for intelligent agents. By learning from experience, updating their knowledge, and refining their strategies, agents can become more effective over time. This process of ongoing learning and adaptation is what drives progress in AI. Evaluating the performance of intelligent agents requires clear metrics and benchmarks. By measuring outcomes against defined performance measures, we can assess how well an agent is achieving its objectives and identify areas for improvement. This evaluation process is essential for developing reliable and effective AI systems. Robustness refers to an agent's ability to handle unexpected situations and continue functioning effectively. Robust agents are designed to cope with errors, uncertainties, and changes in their environment. Building robustness into AI systems is crucial for ensuring reliability and resilience. Scalability is another important consideration in agent design. As the complexity of tasks and environments increases, agents must be able to scale their capabilities accordingly. This may involve distributed systems, parallel processing, or advanced learning techniques to handle larger and more complex problems. Summary: intelligent agents are the driving force behind many advances in artificial intelligence. By perceiving their environment, making rational decisions, and acting autonomously, these agents are transforming industries and shaping the future. Understanding their structure, behavior, and capabilities is essential for anyone interested in AI. As technology evolves, intelligent agents will continue to play a central role in solving complex problems and improving our daily lives.